and it's actually it's yeah, you can basically, if you have the error message, the first response is always like just Google that error message. Most often, like, it will solve your issue, like it will give you hints like what's going on. And if you are still stuck, like you can totally email me, not email me, but send me message on Discord. I will try to help you that way. And yeah. So unless you have very general questions on the homework, like, but if you have like specific questions, like as I said, like there's a error message coming up and so on, like it's much easier, like, and better to send message like your questions like through Discord instead. Yeah. So okay, let me get started with actually basically continue what we talked about last time. So remember, like, we are talking about Harris corner detector. So we have this E function here. So last time I called it cornerless function, but maybe it's better not to call it cornerless function because there'll be a confusion later on. So maybe I just call it this E function here. So remember that what's going on is like this E function is just locally. What you see is like what we're trying to do is like you move this U and V, like have a shift of this original image, shifted by like some U and V here, and then you kind of like just look at the neighborhood, like with this window. So something like you have an image, just you shift it a little bit, and then like you look at the difference at different location, like for example here. So as we discussed last time, like, so if you're at the corner, or maybe like some patches that's going to have um kind of loss of like some of like texture which I would say like have lots of high level high frequency components, then you this E value will be big basically, or like I should say like for all UV there, like for all different direction of shift, you will have like EUV is kind of big, or like, or I should say like not big, but it's like you can just look at 1D here, this as a U and U is zero. You have like more or less like something like that, right? Well, maybe a parabola or maybe not exactly parabola, but it's increasing. Or at least like you have like zero here, but like non-zero elsewhere. Um, if you have, on the other hand, if edges, then what's going on is like you have one direction that is not going to change. Like for example, like in this direction, if I shift along this direction, like my EUV is not going to change. So therefore, like, by the way, EUV should be zero when U and V is zero, right? Because you look at say U and V is zero, then like this is just IXY itself, right? So I'm subtract that is just equal to zero. So I will have like zero definitely when EUV is equal to zero. But if this is an edge, then along one direction, then like uh this is kind of zero like along one direction, like I move along this direction. But for an kind of like direction like perpendicular to this direction here, then this will be um basically non-zero. Oh, actually, I asked this before. Maybe I ask it again. Like, if I have this situation here, basically this is zero, and and for the rest of places here is non-zero. Then what's the edge direction here? Is the edge is like okay? Is the edge like this, or the edge like this? So basically, let's say I have a point here. This is the corresponding EUV. So if I compute the EUV at, at, at this point here or at this point here, so I got the EUV response like this. So is that the edge should be like this way, maybe this call it A here, or this way call it B here. It should be A or B. wow, or everyone says B, but uh, I don't know. I don't remember this kind of stuff. I just try to think about that. So it doesn't, is that really B? I don't know. That's really, uh, so let's see. So I have the EUV like this way. So if I etch like that, I change along this direction, basically shift along this direction. I shouldn't have changed uh on the patchway. So for example, like I shift this is the original image. I shift along this direction as well. So at this point here, and the neighborhood of this point here, it doesn't seem to be have any change, right? So therefore, like along this direction, I would expect like this would be 0. So therefore, it looks like it's A, because otherwise, if I look at this one here, if I look at this situation here, if I try to go along this direction, what do I get? Like I have the original patch is like this. Maybe I shift a little bit, it's like that, right? So one patch is I will have start with like this way, and then next time I got a patch is like that, right? Okay, I'm not exactly drawing right. Yeah. So this look different, right? So therefore, like yeah, um, so therefore, like along this direction, in this case, it will not, for this B case here, it will not be 0 actually. So yeah, therefore, like yeah. So okay, anyway, I have the EUV here. So but as I said, like as we said last time, computing this EUV like directly is computationally intensive. And at the same time, we don't need to know exactly what the function look like. We just want to know the shape, right? So then last time we say, okay, let's try to like expand that with Taylor series expansion. Then eventually we can just write EUV as something like that. UV multiplied by this guy here and multiplied by this UV here. And this we call a matrix M here. And now if I think of this M here, okay, by the way, this is a positive definiteness symmetric matrix. So therefore, like the eigenvalues has to be like positive, and I can decompose that into, and also the eigenvector matrix will be orthogonal. It's basically just a rotation matrix. So then we can diagonalize this M. So therefore, like we say, if I diagonalize this M uh, with so that like M is equal to R lambda lambda 1 lambda 2. Okay, I put 0 here also times R transpose here. Then I just substitute uh, this back into M. So then I will have, I can write this one here, and I can say R transpose UV is U pi V pi, right? So it's just a quadratic equation. It's just an ellipsoid because lambda 1 lambda 2 is bigger than equal to 0. Since like the matrix itself is a positive definite. So then as we said last time, then we want, if for a corner, we want this function to change rapidly, right? When U and V changes. So therefore, like we should, for corner, we should look for like lambda 1, lambda 2 are big, basically. If they are big, then we consider as corner. And also, by the way, like for this guy, in practice, to implement that, you see like we're basically doing like derivative like in x direction and y direction here. So what we can do is we can simply use um uh a so okay, for open zero it's just use a sober filter. Maybe you can use something else, but I think for the its default implementation is just use a sober filter. And then because sober filter is already have like some smoothing effect, right? So then you don't need to do smoothing, then you just specify the kernel size. That will just some how many basically, like for example, what I mean is like after you apply the super filter, then uh, here, like for example, just for this one here, let's say if I apply the super filter at ix here, then I compute ix square will be just element wise product of ix. Maybe I use this as I indicate element wise product, and then for example, if I consider uh this image, like maybe I call it J here, say ix this product here. Uh, if I want to find this value, like just like sum over wxy I square here, like at this point here, then I would just set a kernel size or something like, okay, sum over the neighborhood of this pixel here. So for this window. So what I mean is this window in here, like you can smooth that like further, like with maybe a Gaussian or whatever. But because uh, for software itself, it's already have some smoothing effect here, like we don't need to do that. So then this can be just like you can just specify the kernel size and sum over like this uh, for the um, for the neighborhood. So okay, that's basically then now we just want to determine after we compute this, then we want to see like for each of the point here. Note that this is like after we compute this, like we have this matrix here. So I have essentially for these four coefficient here, each of them will be you can think of that matrix, or like you can think of like for each of the pixel of the image, you can have this matrix coming up. So what I mean is I let's say okay, let me just let's just this is M again. This is M. So for each pixel, like pixel value mx here is a matrix, right? So for each of the pixel is actually a matrix. And for that matrix, we just want to see like if the corresponding eigenvalue is big. So if both of them are big, then that's good. So and in practice, what we can do is we can compute this as kind of cornerness function here. So we define C as something like that, like lambda 1 times lambda 2 minus alpha, lambda 1 plus lambda 2 square. So let me illustrate like this will be something like that, like this is cornerness function. If we change the alpha, so you see like, maybe I change the alpha a little bit, just let you visualize the effect. So uh, in practice, we will set the alpha around like 0.04 to 0.06. So you see, like if I have the for alpha around this range, I have this C function will be like have this shape like this, right? So as long as I have C here, it's like bigger than like somewhere like I don't know what's this value here, but uh uh say 0.01, I don't know exactly. So then if I say like the C is bigger than 0.01, it will be basically everywhere like around here. So therefore we can just compute these C values here, and then I say if like C is bigger than certain things, then we'll say it's a corner. So for if C is less than if C is small, then it will be like something either an edge or like flat region. And then basically, I guess wait, let's see, that's basically what Harris corner detector, the entire thing is. So as I said, like we have this start with an image, we need to compute the M. So M will be like basically computing the super filter along X and Y direction, and then like we are going to sum the values for each pixel will sum over like a neighborhood, average over the neighborhood values. And then so this is like the image gradient. So that try to compute the M, and then smooth out. That's basically okay. Yeah, he is here like with implementing like in the sense like derivative and then like doing Gaussian filter. But as I said, like if you look at the OpenCV implementation, like it did specify just the kernel size and the super filter. Uh, what do they call like I forgot, like, but the super filter, like smoothness, something, right? So, uh, but anyway, like this, you can implement like this also, like if you really need to implement from scratch, but you won't most likely. So, but what I mean is like why I'm saying this detail because in practice, the parameters that you use in super filter, like, you need to understand what's going on to understand to even though like in practice you can just try and error, but it's good to know like what those parameters actually mean, right? So and then finally you get this C value. Of course, you can adjust this alpha as well. And then like for this C value, just see like if it's sufficiently big, like these places we will consider as corner. And finally, we can do some non-maximum suppression. That's simply for example, this is a large C response like that. So the log maximum suppression will be just, uh, oops, where do I have that? Okay, it doesn't matter. Like, so the idea would be just like we want to make sure it's like the maximum. So one easy thing is that you can just check like with, for example, look at any point here that corresponds to be potential response, and then if that point, I would just look at the neighborhood of that point. If like it's larger than all the neighborhoods there, like the A neighborhoods there, then I would consider that point as a maximum. It's a valid candidate. Otherwise, I would just reject that. So if we do that, then we can reduce a lot of this response into something like this. So that will be the final result for Harris-Corner detector. So that okay, maybe just a remark here, like there's other variation of like corner detector. For example, like we have this Shi-Tomashi like corner detector. It's very much similar to like Hertz corner detector, but rather than like computing this C here, so it just want to make sure that this so it's just like trying to take this region basically. You remember the C function is more or less like kind of smooth like this, but they just like take C function as a minimum of lambda 1, lambda 2. So then you have something like that, and then you make sure that this C is bigger than this lambda mean. So therefore we have this region like that. And by the way, another remark, like for this C function here, um, uh, you don't actually need to uh, diagonalize, I mean, compute the eigenvalue of like this M matrix, even though it's very easy. Uh, but knowing that the product of eigenvalues is actually just the determinant, and that the sum of eigenvalues are just the trace. Um, so uh, so therefore, like, by the way, do you guys know determinant and trace? Like, maybe I just test you guys. Like, so okay, I need to pull back the. So if I have something like 2, 1, maybe see, maybe like that, 2, 1, 1, 1. Uh, what's the determinant? Uh, okay, that's good. Yeah, you know what's determinant. So determinant is like this multiplied by this minus this multiplied by this. So it's like 2 times 1 minus 1 times 1. So and do you guys know what's trace? Trace for this one. So you may want to. Okay, good. Yeah, trace just at the diagonal. Yeah. Um. Yeah, that's a nice linear algebra results that it's good to know that your eigenvalues, the sum of eigenvalues is actually just the trace, and the product of eigenvalues is actually just the determinant. So therefore, here also instead of need to diagonalize that, we can just simply compute this. So for example, you have uh, the matrix is M. Let's say this is a M11 M12 M21 M22. So I can replace this by M11 M22 minus M12 M1 at M21. Let's say, and then this will be M11 plus M12, something like that. So I guess maybe that's the reason he original Harris Corner Harris uh derive. I mean um suggest to use this cornerless function because yeah, he's thinking by doing that we don't need to do the what I want to say we don't need to diagonalize we don't need to find the eigenvalues of m here. Yeah. um so but it turns out it's not so difficult. So then um what she Tomashi does is actually more lateral, I guess. But still I guess Harris corner detector probably more more famous. So it's probably the most famous corner detector uh, or most popular one. Okay, so let me just give maybe a uh, where is that? Need to find the. So let me give an sample of Harris corner detector. Maybe okay. I guess it's oh okay. That's not good. I guess it's better. I still not move this thing here because I may have the solution of something. Okay. Let me just again start a new maybe a title. Can I use a title here? Yeah, probably is okay. So let me just copy the code here. So I have a Harris corner detector for okay. This is a interesting views in my lake. So let me see. So here uh I have the Harris corner detector that I use the trackbar that just for convenience. So okay. Um the actual detector is here, calling this corner Harris. And you see the parameters it asked me to fill in here. Let me if I move maybe a little bit bigger. So the 0.05 is the alpha there. And maybe I also let's see. Oops, why is not coming up? Oh, okay, yeah. I probably need to, okay. So you can look at the description, like the API. So we have block size and kernel size, and yeah, K is yeah, K is you see is actually the alpha there, and the kernel size. What is that? The kernel size uh is the aperture parameter of the operator. So uh okay, I that one you may want to dig deeper, but I think like that is like basically like the filter size of the super filter. Um, so you and that one has to be odd. Actually, it has to be an odd number. Um, and box size is let's see, box size is here. Box size is you sum over so uh the neighborhood. So it's like the window size there. So, but anyway, like in practice, it doesn't actually affect too much. Uh, let's see, I'm not varying the alpha here. Alpha is doing the same thing. Uh, the things that can vary the most will be like the threshold. So, here, like we just pick the threshold as uh, you take the maximum response there, and then I take the ratio of the maximum response. So here I start with like 0.01, like 0.01 of the maximum response. So you see like it's something like that. If I change the, let's see, um, if I change the box size, so it's like something over like it just make the basically make the dot bigger, because like if you think of like some over the a larger neighborhood, then like uh what's going on is like if I have a, if I have a corner here, this is a corner, then if I sum over a larger neighborhood, then like even a some patches like farther away will be catching this corner, right? So that is quite reasonable. So if you increase the kernel size, then basically it's just we will get more response. Um, and the second parameter, like modifying the subfilter aperture, is actually does not change too much. Like so, I guess you can use the default. I guess the default is a 3 there. It doesn't matter too much. And the threshold matters a lot. Basically, if I change the threshold, then of course the larger threshold will catch less uh, carve corners, right? So okay, yeah, I guess that's it. I more or less that's all I would like to talk about for Harris corner detector. So I guess we will just move on. So let me, so so let's move on to talk about something related. So we'll talk about local features. So actually you can think of like corner as some kind of local feature as well. And these local features are useful in, for example, like a very kind of probably like a popular and the killer application will be like just doing feature map matching. So for example, you have some local feature, like I have these two image, one of them is got two images, one of them are got rotated. Then maybe I want to find the orientation of this one, how this one is related to this one. So what we can do is that we can find some feature first. So like let's say this is the feature points, and we're trying to match those feature points. So so the feature points is also known as the key points there. So we want to find the location of these key points. And then after we located these key points, then we want to be able to kind of like represent those key points. So it's also usually known as this descriptor. So you kind of like generate some like local descriptor for these points here. And hopefully we want this descriptor will be kind of like invariant in many sense. So for example, hopefully in this case, like it will be like rotational invariant. Like even though like the descriptor like original is like this, after rotation, it still like represent something like this. And also like we want it to be scale invariance for different scale. It's still like the same representation. So therefore like so that we can make sure it will be like still the same, more or less the same thing, right? So we can match them, right? So and then of course afterward we have this descriptors, then we can match one by one. So then maybe we are able to match this one with this one, this one with this one, and so on. Then by solving some linear algebra, we'll talk about that next time maybe. Then we'll be able to find like what's the uh, how the image kind of like oriented like from one to another. So I mean, this kind of matching have lots of applications, and like for example, you can do it for alignment, for 3D reconstructions, for tracking, and even like indexing. For example, you have some objects that you just like you want to find like very precise objects. For example, like I have this what's that called like this statue of the liberty like that, like maybe I just want to look for that like from a bunch of images. So then like one way I can do it is like maybe I get all these local features, and then whenever I have objects have this kind of like local features, I will just consider that as the statue of liberty. And in the same manner, it would be like can be used for object recognition. And so yeah, we'll talk about that later on. Like so, with this kind of matching, we can compute the orientation of two photos, like to get uh somehow like how they are actually oriented, like basically like the cameras, how the cameras oriented from one another. Um, and structure for motion. That's is actually uh more evolved topics. I probably we won't go into detail for that. So it's like um, you kind of like get from a bunch of photos trying to get a 3D model out of this bunch of photos. The fundamental matrix actually describe how one so you think of like you have a scene like captured from two different views. In a large shell, the fundamental matrix like describe how one view is kind of related to another view. Yeah, but then more than that, you need to go into the math. We will talk about that later on. Like, don't worry about that. Yeah. So, but not discuss, but yeah, later on. Probably when we talk about CAM model. So my plan is that after we talk about maybe some tracking and then like also like optical flow, then we'll talk about the CAM model. Then we'll talk a little bit about the fundamental matrix and so on. Um, and then so okay, in terms of Harris-Corner detector, we see that the Harris-Corner detector is also like some kind of local features, right? So but know that like it's just doing the first part. Like to do the matching, we need to have determine where the key points are, and then afterward we need to have the descriptor as well. So the Harris-Corner detector only do the first thing, it's like determine the where is the key points. Then we need to determine also the descriptors. But even for the first step, um, it's not clear actually. Like you can definitely use Harris-Corner detector, but it's like uh, it okay, maybe let's before that, like we said we have these key points and descriptor, right? So let's think of like what are the good characteristics of this local feature, uh, kind of like local features. So I for the in terms of the key points, we want that key points to be repeatable and local. Eh? Repeatable means that okay, pick this key point here. Um, if I from another scene, I should be able to find the corresponding key points. In this case, not so repeatable, I guess. So, and in terms of locality, like we don't want to be a key point. Let's say if the original key point is here, but it's specified like somewhere here, then won't be too useful. So, and for the descriptor itself, it want to be salient. Uh, I guess the salient in the sense like it should be unique. For example, like if I have this descriptor for this key point, like for this location, and the descriptor for this location should be sufficiently different from one another if they correspond to two different points. And also, I hope the key points is kind of, sorry, the descriptors will be kind of compact, so it shouldn't be typically the length of the descriptor is like 128, but it's like, yeah, it's often like this size. But you don't want to be the descriptor is like maybe like a million, a dimension million, then it won't be very efficient if you want to do matching. So and so here's another graph just elaborate, like we want to be repeatable, right? Like this one. So if I have like one scene I get something like this, another scene I get like points like this, then there's no point of trying to matching them, right? They're just not repeatable. So now we focus on the detecting the key point first, right? So in terms of Harris-Corner detector, so think of like as a just a trying to as a key point detector. Yeah, maybe I ask a couple of these questions. Yeah, I don't know. Maybe I ask one of them, just one of them first. Uh, okay, that's again, it's very difficult to draw anything, but it's okay. Maybe I just say circle it now. So is there a rotation invariance? Like, do you think Harris corner detector in terms of detecting is that rotational invariance? Rotation invariance? Does it is it rotationally invariant? I should say. From what we understand like how Harris corner detector work like earlier, is that rotationally invariant? So some of yes and no question here. Yeah, yes will be meaning that like I rotate it, then I still catch the same key point. Yes, this would be yes, right? Because you think of like it's a corner. I don't know. Oops. Okay. Like for example, this is a corner. If I rotate it somehow, it's still a corner, right? So I still should be able to catch the same corner there. Now, how about scale invariance? Is another question. Okay, you probably like these two questions are too close. You want to give a kind of indicator that like which one you're answering. So for scale invariant, is that also uh okay, also yes, it's okay. Yeah, we put a two there or something like, yeah, that would be better. So yeah, oh, please don't put yes. The TA is not going to figure out like which just yes, he's not going to figure out. Yeah, that two is okay. Or like yeah, or two yes, or like scale yes, or something like that. Otherwise, the TA cannot figure out like which one you're answering. Um, okay, yes, that's great. So actually, but however, your answer is incorrect. So what I mean is like it's not actually scale invariant because you think of like if in a smaller scale, you think of it's a corner. If you zoom in there, it doesn't really consider as corner anymore. Like this one here, if you are kind of sufficiently shrink zoom out, this one will look like a corner, right? Like this one here. If I zoom in a lot, okay, this really very hard to draw. So zoom in a lot, I may smooth out this thing. Then in every places here, like it will not be considered as a corner. Um, Oh, I appreciate you guys' honesty. Like even I gave out the answer, you still say yes. Great. Okay. So let's continue. So then the thing is like we really want to okay, one thing is like scale invariant is great, right? We want to have scale invariant, right? Because as you see earlier, we have these images. For example, like I guess like one of these example, like this is not obvious like this one, but still like this one is a bit bigger, right? So we want like if this is much bigger, we want to make sure that like it was still able to catch the same key point. So therefore, we want to have like some kind of scale invariance. So okay, so how do we do scale invariance for keypoint detector? So the way to do it is like you try to just consider different scales, and then we use some kind of like signature function that only consider scale that with the maximum signature. So for example, I have two images here. I would design some kind of like signature function that like at a particular scale, it will give me the highest response. And then I would just figure out, I will basically will just consider uh, for example, only at that response I will consider the corner. So then we will have a base kind of like a scale invariant uh, feature detector or key point detector. Yeah. So so like this, if I have some kind of signature function here, like if I for different scale, if you look at that at different scale, like here at a particular scale, I just maximize here. Like here, around here, I got the maximum response. Then I would just like focus at this scale level, and then it's drop where it drop. Then I just focus at this scale level. And for this different image also, like I look at like different scale response. It peaks somewhere, let's see, somewhere here. Okay, it isn't showing the peak here, but presumably like they will peak in the same places, so therefore it will be scale invariant. So then the question is right afterwards, like how do we what kind of like signature function, scale signature function we should consider. So a function it turns out work quite well would be simply doing something like this second hat. It's just like the second derivative of this Gaussian. So it's like uh, something like this. So it's like the Laplacian of Gaussian. Uh, you see if I have this Laplace of Gaussian response here to apply to this different blob size here. So I have this one get maximum response like at this scale here. So it's like, and if I have a bigger blob, then the response will be like the maximum response will be like somewhere here. If I still have a bigger blob, I have a response here. So uh, okay, you see like okay why I have the response at a different region because I have this Mexican hat here. If you just think of blob, then if this response is too small, if I look at that, this thing like if the entire thing, okay, maybe I look at this one here. The entire thing is like sum up to zero, right? So if my blob is that big, okay, yeah, the blob is that big. Okay, this is just showing 1D. Then when I sum all this value, I will just get zero, right? So and if the blob is too small, it doesn't get the peak as well. So the blob will get maximum response when the size is something like that, right? So so it'd be like here is I get maximum value here when just outside this region here. It's okay. Like this is off here. I guess I'm not going to spend too much time on this. So, but anyway, if I use the Laplace of Gaussian, then I can use the Laplace function of Gaussian as the signature function. So then a very kind of like uh, kind of a lateral solution will be simply like I apply Laplacian of Gaussian at different scale, right? And then like for the maximum scale, let's say I at the maximum scale, I also like along that scale, I will apply the Harris-Laplace detector for the image at that scale. Then in the sense that you can think of this, actually we have a three-dimensional structure here. So we're trying to find the maximum in this three-dimensional structure. So in the sense that it's both maximized across the scale. This will across the scale in terms of the okay, this level will be maximized according to the uh, uh, signature. And then this one will be according to the Harris. And then we have this so-called Harris-Laplace Laplacian key point detector you can think of. Um, And but this is a work like about 2 decades ago. Uh, Here, but we want to elaborate, like to talk about like one is like really famous is like the SIFT. Uh, that's basically like more or less the same idea, but instead of using the Laplacian Gaussian, what Low did is like basically the author of the SIFT paper uh, is like he approximate the Laplacian Gaussian using difference of Gaussian instead. So difference of Gaussian is basically like you apply Gaussian uh, smoothing like to image with different sigma, and then you just subtract with different scale. So and that you see that like Laplacian is like this, difference of Gaussian is like this. It looks quite similar, and so we can approximate the Laplacian of Gaussian with like difference of Gaussian. And this turns out to be implemented more efficiently doing that. So in the sense like what uh, SIFT does is like we have the original image, we smooth that with some variance, right? Then we compute the difference of Gaussian here, and then take the next, take the like smooth image, and then like further convert it with a larger uh, larger sigma, and then again compute the difference and so on and so forth, right? Then you have this will be like approximation of the Laplacian of Gaussian, but this is actually a difference of Gaussian. But we can use this as a signature function as well. And then in that sense, we're just trying to find the maximum, okay, in the same thing. Along the scale, like we will try to along both like the scale dimension and also like for the x and y dimension, we're trying to find the local maximum, and that would be our key points. And so that's essentially be the key point. Like for example, for image extracted, like using difference of Gaussian. So it'd be something like this, and this bigger circle here will be is here is just visualize illustrate that uh, the biggest circle correspond to like a larger scale. And I have I have this result like this. But it turns out that you have lots of response if you just use different Gaussian like this. And no, in the SIFT paper, he mentioned some kind of trick for outlier rejection. One thing he did is he just did a Taylor series expansion like for the candidate. So because you can compute the gradient and also the second derivative at each point there. So this is just yeah, okay, yeah, you just approximation like using like a discrete derivative as we talked about earlier. For example, like for the first derivative, you can do the super filter, and this second derivative also you can design another filter for that. And with that, you can approximate the do a Taylor series expansion like for any point there. And then let's say we start with like a point that considers the maximum candidate, then we just try to like find a better approximate by doing Taylor series expansion. So if you solve this equation here, I mean, basically based on this one, you can find the maximum value for this quadratic equation, right? The maximum value would be at this point here. Then you just iterate. Basically, you start with like the point here, then you approximate the next iteration is like equal to this guy here, and continue to do that. And if this does not converge, then you would just say consider a failure. It's not exactly a maximum. And if it converge, also like it's something a pretty ad hoc, but it's just like trying to see like if it's like kind of like smaller than some threshold. If it's a smaller than some threshold, then it's also going to be rejected. Um, so another trick to do outlier rejection is essentially the same thing as Harris corner detector, because we can also compute this M matrix like, for that thing. So yeah, it's essentially this is just the M here. It doesn't have the smoothing here, but if you do the M exactly, you will just have this further smoothing that. So we compute the M, then we know that like for the M matrix, is corner only when like lambda 1 and lambda 2 is both of them are big, right? And in this case, we want to excluding edges because edges won't be good features, right? Because you think of like this as an edge, uh, you can have like it's hard to localize, right? Because like you may catch somewhere here, but maybe in another scene here, like this probably will be the key point. So edge will not be a good local feature. So we want to exclude edges. And we remember that like for edges, we will have like one lambda is bigger than another lambda, right? So therefore, like what we can kind of how we can identify that we can evaluate this function here, the trace h squared over determinant h. So that would be equal to this guy. Then let's say if I want to set a threshold that like r should be not bigger than, or r is basically just the ratio of like one lambda um, lambda 1 versus lambda 2. So we want to say r should be less than 10, let's say. So then the result I should get should be yeah, if you look at that, this guy is actually just equal to r plus 1 over r, right? So because like, this function itself is monotonic, so say if I want r should be bigger than, should not be bigger than 10, then I can just compute this one, this value here, and make sure that this value is uh, is not bigger than 10 plus 1 square over 10, say. So if like bigger than that, then I will consider this definitely is an edge, then I would reject that candidate. So so that's basically how SIFT does for kind of keypoint detect keypoint extraction. Let's mention also one other like keypoint extractor. This is known as this maximally stable extremal region. So what it does is a pretty simple. It just use some watershed segmentation algorithm. So the watershed segmentation algorithm, like okay, we, we won't go into detail for this one. So basically, it's just that you set a threshold. It's like throwing water into the uh, to I shouldn't say throwing, like pouring water into some uh what should I say? So okay, maybe I should put it like this way. So I have this image here. Uh, okay, I didn't prepare for this, but I just give a high level. So maybe my description won't be precise. So it'll be something like if you think an image, the intensities can be like can be considered as a terrain, right? So if I have high intensity, so it'll be larger, than low intensity, it'll be smaller. So I can match the image according to the intensity, right? So say if I have an image like this, just maybe what should I say? Maybe I just have like quite dark in the middle, and then I get like lighter around that, let's say, right? Okay, and maybe even lighter. Okay, okay. This is different color. I'm sorry, like for so then for example, for this image, it would be something like if you think of this as a function of intensity, then it would be something like a value, right? It's actually and then like you can do a fresh kind of like segmentation by kind of pouring water. Like you can think of pouring water into this thing here. Then it will actually segment the image, right? So like if it's a at up certain water level, if there's places that fill with water, then I will kind of like segment into uh, one set, and then in that case, like for example, if I pour in some water, then maybe I will segment this place here, okay, versus all these other pixels. So and if you pour in a different amount of water, then you will have like different level of segmentation, right? Like this one. So if I pour in more and more water, then I will have like segmentation like originally is like okay, like it's all dark outside here. Then if I pour in more water, then maybe it's the other way one. Then I actually I guess it's a inverter. It's okay. Like it's yeah, but anyway, like so what I mean inverter is like this here, like comparing with my example, like this bright spot is a high level, I guess. It should be the low level. It's like it should be the low value here. So if you pour in water, like I first fill in this places here, right? This is low values here, and if I pour in more and more, so then it's just like go away. Now, if so, this key point extractor basically is just like you consider a range of segmentation parameter. So different level of water, like you different amount of water you pour in, and then like if you have region that is not going to change for that range, then we'll consider as a descriptor. So then like we'll have something like this is some example extract like this will be the region as a descriptor. Okay, this so much I like to talk about for descriptor. Then afterward we sorry, like this not descriptor. I so much I want to talk about the key point extractor. So now let's talk about the descriptor. Like once we have the key points, we need to describe that, right? So a very natural things to do is like we can just take a template, right? For example, like I take a very if I want to find the descriptor for this pixel here, I just take the entire neighborhood as the descriptor. But that's apparent that's some problem. Okay, first thing like okay maybe like again like uh something apparent, but like just to see like you guys are still here. Uh, so say if I have this point like is the key point now. If I take the descriptor, let's say I as I said like I take this descriptor as just taking the neighborhood. For example, like I have this key point here. Um, I take the neighborhood like uh of 11 by 11, right? 11 by 11 neighborhood. So I create a vector of like 121. So as my descriptor. So uh for this descriptor, will it be rotationally invariant? So anyone here? Okay, you sure like it's not for this particular case. Like, for example, I don't mean that has to be a dot. It can be anything. Like for example, this can be yes. When we say the rotational invariant, it doesn't depends on the patch. It depends on the 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 method of the how you I mean depends on the how you generate the descriptor. Yes, it won't be rotationally invariant, right? Because if I just consider this as extract the labels, apparently like if I rotate this thing here, for example, I rotate this cross into like this, the descriptor will be totally different, right? For example, like this will be like dark value, this will be zero, right? At these places will be zero. Um, at least you just look at the first row, like apparently the total thing will be different. Like, and how about, okay, like this is a question 2 or something like that. Give how about scale invariant? Again, you want to put some uh indicator or something like that is like an answer for like question 2. Yeah, okay, yes. So yes, it won't be. Answer is no as well, because if you scale it, apparently it will be not the same also. Like if this guy got scale it, maybe it got thicker like this, like it won't be. So therefore, like if you just take a template, it won't be a good descriptor, or it will be pretty bad. So it's not scale invariant, it's not rotational invariant. So so what do we want to do? Like, so we want to generate something is like scale and rotationally invariant. So a good way to do that, like is a uh using histogram, um and let's see, wait. Okay, I do it. So okay, this is a key slide here. Uh, to understand like this so-called histogram or and gradient. This is an important concept. So basically, let's say like here is the key point. I want to figure out like what's the what was the descriptor for this key point. Now what I can do here, like as you see, I will take the neighborhood like with a window of like 16 by 16. So I have uh basically have like 16 by 16 pixels here. And for each of these 4 by 4 block here, I can compute the gradient for each of these pixel here, right? So I can compute the local gradient. The local gradient will have like two values, right? Because the gradient is a vector, right? So it will have the direction for each of these value, right? So here I don't care about uh, the magnitude of the gradient. I just care about the uh, direction. So therefore, it's called like oriented gradient. So I just care about the direction, and I want to kind of tally like what's how many directions like for, I mean how many pixels have like some corresponding direction. So therefore we compute a histogram for that. So therefore, as you can see, like we will just kind of quantize all the directions to A, B, and C here. So I can have like this direction, and so on. For example, if I have direction like this, most likely I will quantize to somewhere here, right? So let's see if I can I can draw a little bit. Okay, I don't know why only mouse allow me to draw. So for example, like I have like somewhere like okay, this is horrible. I cannot draw with mouse. So if I like point like this, then it will be like quantities into this pin, say, right? Then uh then you can count how many, for example, like this guy here, you see you have more direction like pointing into uh all the way like upward. So then basically you have a histogram. Essentially, like for each of these 4 by 4 patch, I have a histogram, right? So now I have a histogram of that. And then like for this histogram, I can uh I I can consider this histogram as a feature, right? And then that will be because I have 8 bins here, I have 8 values here. So for each of these guys, I have 8 values. So then in total, okay, maybe again a question just to see you guys are following me. Uh, what's the dimension of the descriptor here? that's the number of element of this descriptor. I cannot write or draw or something. Can I? Maybe like number of element of a descriptor per pixel. So that would be like the dimension of descriptor. Right? Actually, you read the slide, this answer is in the slide, but how many you can count, right? But like again, it should be a it should be a simple question if like you are following me. So I have so I can take the histogram as my feature, right? So for each of these 4x4 block, I have a histogram. And then I have 4x4. This is just counting, right? Then I have 4x4. So many blocks here. So what per pixel? Okay, per pixel I have 4x4 block here, 4x4 neighborhood block here, and each of this block here, I have a okay, okay, yeah. So someone give a correct answer. Uh, uh, yes, you have to count everything. Yes. So we have like for each pixel here, right? You have like 4x4 patches. Sorry, yeah, 4x4 so many patches, and each of this patch I have yeah 8 features correspond to the 8 bins of the histogram, right? So therefore, like if you multiply all together, like, it should be like 128. And so that's basically the key point. So we can make a slight modification. Just make the kind of scale down like the influence like for block that farther away, right? So for block farther away, probably this one should not be counting as much as this one, right? So what we can do is like we can has compute a histogram like for the entire feature, but we scale down that like for just apply like a Gaussian filter for feature that's like far away, then we just like get a smaller value, something like. So okay, that will be a histogram or and the gradient feature. This is almost like the SIFT descriptor already. So there's some slight modification. For example, like for the one we had described just right now, it's not actually a shift invariant. Sorry, like rotational invariant, because like if I just take a patch here, if I rotate it, right, then I will have a different orientation of the histogram, right? So what we can do is I simply uh, order the histogram. Uh, so for example, like we can always like make sure that like the largest value in the histogram is like is the first bin. So basically we always say if like this one is the maximum, we just shift that like so that this one is with the maximum. So then in this way, then like you will get the uh, you also get the rotational invariant as well.
Dr. Chen, I have a
Yes.
question.
Yes.
So in this case dimension, what's the dimension then? Is it 8 or 128?
128. Here I'm just illustrating one block here. So one of the patch here. So what you can do, what we should do is like we can go through the entire histogram and then pick the yeah, actually you can do variation of that. Like one possibility, you can go for the entire histogram and then pick the one that is like the one with the largest value, and then always make the one with largest value as the first bin. Yeah, then yeah. So yes, basically, if let's say like this second, okay, let me go back. Let's say this second one is like the largest bin, like or the bin with the most uh most gradient. I'll fall into this bin. Then I will just say shift this one, like for add each of these patches here, like we will just shift all of them like to this one. So basically for all of this guy here, we'll just shift the histogram to the second one. So then in the sense that it not always get the picture like this, like, but yeah, conceptually it's like yeah. So yeah,
But,
I guess you can do yes.
yeah, but actually there are only 8 directions, different directions, right?
Yes, there are only 8
With
different
8 pins.
directions. Yes.
Okay, so then the dimension is just 8 direction more times the number of pixels of the images. Then you can get a histogram, right?
Oh, wait. Let me go back to here. I guess you're asking. Oh, shoot. Okay.
But I think you asked about the number of dimension per pixel.
Yes,
I
per
mean, the
pixel
number
is
of
like
elements per
it's
pixel.
128. Yes. I guess let me go back. By accident press something. Okay, I guess I almost times out. I guess I'll just clarify this, then we'll stop here. So okay. I know that like for each this guy have a histogram, right? So each of this guy here, the histogram have 8 bins, or you can compute histogram for each of these, and then we'll get like 8 bins, eight numbers here. And so, and for each of these pixel, like keypoint, we'll look at, we have this, each of these neighborhood patch will compute this histogram. So therefore, like each of these will have like 8 features. So it's like the total number of features is 4 by 4 by 8. So that is per keypoint. Like per pixel, I have 4 by 4 by 8.
Okay.
Yes. Yeah. Yes. So okay. I guess I will stop here. Uh, and entertain any questions. It can be like questions about this one, or like questions about like the homework. But if it's like some you got an error like for particular command, as I said, like probably it's easier to send me a Discord message.
I have a question.
Yes.
So for the import CVUI,
Yes.
do we need to like install another driver for that, or does that come with CV2? Because I'm having issues
Okay.
with
Yeah,
it
I think
reading
you
it.
need to install that. So, but it's very easy. Like as okay, let me just yeah. Uh, yeah. You can. I think you can install that. Let's see. Yeah. I think you can install that. So any
Okay,
other
thank you.
yeah, okay. Any other questions? So I hearing no question. Let me try the chat. So someone have a question. I unable to see my homework too on Canvas. Oh, okay. Do you when you go to Canvas, there's a link, right? Is that is what you mean you cannot find the questions or homework too? This should link to the website basically. It should just link to here. So the question is here instead. Oh, I forgot to add a submit button. Okay, let okay, yeah, I that happens sometimes because the default is that default setting is a no submission. So sometimes I forget to let me just put it back right away. Uh, so any other issues?
I have a question.
Yes.
For homework two, the second question,
Yes.
do you want the two pictures to overlap each other or just sitting next to one another? And then do the Laplacian pairing?
They should yeah, you can do up okay, left, right, top, bottom is okay. Like in the past I have like students submit top, bottom merging, like it's okay.
So what I'm saying is like do those, like for example on the first one you merge those two pictures, right? Now do you use the same picture that you merge, the resulting picture, which is the one that is merged, and then do the Laplacian
No,
pairing
no,
on?
no, 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 no. Just separate things. Like you do start with you can use like different images, even like
Okay.
yes, yeah. So,
So
but
you just put
yes,
them next to one another.
yes, you don't add okay, yeah, yeah, that would be too much effect at the same time. It's hard to visualize, I guess. So you can use the same original images, but start with original images to merge them together.
Okay, I guess I'm still not getting it. So let's say you have an orange and an apple right now. So
Yes.
you put them right next to one another, and then you do the Laplacian of both pictures. Is that correct?
Oh, okay. So you mean the how you did that? So it's not okay. That will need to go back to.
So what I'm looking at right now, that's how you want it to be.
No. You don't just like put them like so. If you put them that side by side, you get something like that. This is not what we want.
Okay.
Yeah. So what we want is like we need to get image, then you decompose the image like with uh okay, I still okay. Let me finish this question first, and then like someone say there's like some problem with Canvas, but like Canvas, you don't worry about that. I will solve that. Like if you cannot submit anything or something like that. Let's see if I need to find the slides though. I think like what's that called, like resampling. I'm not quite sure actually. Yeah. Yes. So what's going on here is that you should generate Laplacian like for both image, right? And then like for the Laplacian, like for each of the level, like you keep one side from basically you have like two. Maybe this maybe it's still like maybe easier to draw. Right, so you have an apple and orange, you decompose that. So decompose that into like kind of like Laplacian, let's say maybe like 3 levels. I have like this also like 3 levels here, right?
Okay.
So then for each level, you need to merge them. So for this level, you have like this one side and this one side merged together, right? So you get something like that, right? And then next level, you do the same thing, right? And the next level, you do the same thing. And then afterward, you merge like this thing together. So the pyramid you can get is like a invertible like operation. So from this one, you can go back to this one here. Right? From this one, you go back to this one. And
Okay.
when you generate this level, like you create these levels, this can go back to an image, right? You combine all of them to create back the image. That will be the image that you see like the effect here. So I'm showing it's just number of level of decomposition. If I do one level, it's like something trivial. That essentially is not decomposing, I guess. Then so therefore like I'm basically just stitching like two images. I just put them together. But you see if I increase the number of levels, apparently like they kind of merge like pretty nicely, kind of like.
So basically, this one is that's what we're looking for right now, something like
Yeah,
this.
that's what we want to do. Yeah.
Okay.
Yeah. So.
And then from there, you do the pyramid with it. Like you kind of break it down and then do the, okay.
Control the level, just check if I'm understand. Yeah. You use the track bar to control the levels. So yeah, so this is like the exact solution that I'm looking for. So like you control the level, then you see like yeah, different the level. If you want to do the extra credit, yeah, that's control the level, you get the yes. So for canvas, yeah,
I have one question when you're done.
yes.
So when you do the when you break them down to, like, I think you said 5 picture, 2 to the 5th, right? Now, do they come out in one picture, or you just can you put them in one picture itself instead of having like 5 separate picture come up?
No, you cannot. It would be like 5 pictures.
Okay. I was just wondering. Okay, all right then. All right, I think.
If we take once we get the 5 pictures, do we take a screenshot of the 5 look, or?
So you get the 5, like if you use the, yeah, you get the 5 pictures that you want to. So what's your question really? Like, I guess I don't actually got.
So once we're able to generate the 5 pictures, we just take a screenshot of the 5 pictures.
You mean you just yeah, we just merge them together? So
do you just line them up and take a screenshot of them? That's what you meant?
Yes, that's what I meant.
So so okay. So think of like any pictures. I say like this is the picture here is just maybe I give like exact number. This is like just picture size, like maybe 120 by 3 here. That this picture here is really just a kind of a 3-dimensional block here, right? So it's a dimension 128 by 128 by 3, right? So maybe I call this A here, and then I have this one. I say also have size B is a 128 by 128 by 3 here. So what I want is I want to take 1/2 of this guy and 1/2 of this guy and merge them together, right? So then let me give you the MATLAB syntax, say, okay, because I on top of my head okay, now let me try to do the NumPy syntax, but I could be wrong. So you can do H stack. So I think it's like just 1/2 of this. So 1/2 of this will be like A, say to 66, right? 64, right? And then 128 3, and then 1/2 of B, maybe something like that. Oh, sorry, like I probably don't even need the not 128. I also star. Yeah, my issue here is I'm not sure it's like this index or this index, because let's see, horizontal, the first index. Yeah, probably it's all right. Yeah, probably it's all right. Yeah. So then you have the new image, is the merge one, right? Maybe I call this one is C here. So but yeah, don't take this literally though, because your image size won't be like this, and yeah, I could mess up the syntax also, like, yeah. So, but yeah, this is the, you can think of this as like pseudocode, like kind of merge like two matrices together. So I look at the assignment 2. For the undergrad session, it seems like there's no problem. Maybe I let mess up the grad session. Let's see.
I also have one more question. It's more about part 1.
Yes.
So referring it to the example that was given with the Marilyn Monroe and Albert Einstein.
Yes.
So mine, are we supposed to also perform? So I know the high pass is supposed to be the image that is like you can actually see closely, and then the low pass is the one that you can see from far away. Is that correct? Or am I getting those mixed up?
Because when you do the high pass, it looks really dark though. I don't know, is that normal?
Yeah, so like the high pass looks like just like an outline of the image, and then the low pass is just it looks like the same
Blurred.
image, just a smooth
Blurred.
filter.
It's more like blurred, yeah, right?
Yeah.
For the pass.
It just doesn't, when I try to go with like the Gaussian filter, it just doesn't look like the Albert Einstein and Marilyn Monroe.
Mine either. It just because the high pass is so dark and it makes it look a little bit different. So that's why I was wondering, were they using high pass or different type of filter? Because high pass would kind of throw it off.
You need to play with the filter quite a bit, honestly, I guess. Let's see. Let me see if I can find.
Yeah, because with the kernel size that we were talking about yesterday, I believe it was yesterday. When I attempted that, it doesn't seem to really change the image too much. And I did try 3 times the sigma, and I even tried like bigger than that.
Oh, okay. It's not 3 times the sigma. Like kernel size is like you need to change the sigma. The kernel size is like not okay. Yeah, I messed up. I just realized that I didn't put the homework assignment for the even for the graduate session at all. Okay, so that I hope they won't be really mad at me. So let's see. Let me find the. Okay, my cat is not really happy as well. So let me find my demo again. Like what is it called? Like it's getting too big. Yeah. So let's see. We have the. You're talking the high pass is too. Okay, this is my low pass here.
Yeah, so currently what I'm experiencing is I only did, am I supposed to do the Gaussian filter on both of them or on just the one that is supposed to be like in the background?
Type both of them actually.
Okay.
Even though like the high pass here, so especially the low pass, I guess the low pass is important. And so for the, I guess for the command that you're talking about, let me find the. So for the Gaussian blur there, let me maybe move to somewhere, see if I can find. I have yeah. Let me from here. So So we have this kernel size and this sigma. Sigma is the one that changed the filter strength because, but the kernel size is really how big the filter. So you can think of like the filter is like something like, let's see, I don't know where I mess up with the pen. Okay, here. So for example, if I sketch it in 1D, right? If you have like the filter is like wider, then it would be like a kind of like stronger low pass. So for example, like if like this would be like stronger than like this. So the kernel size is like where you cut off. For example, like you cut off here, you can make a filter like this, but you cut off here. But if you typically want to get the entire Gaussian, like decay like near the end, then you should have the kernel size like about 3 times of the sigma value, right? But you need to change the sigma. Sigma is the main thing. You need to change like the sigma size to get like different strength of your filter.
Okay. And just to clarify, because I know you probably answered this, but we would need that to be put on both images. And
yes.
okay.
So the one, but know that like the one that you want high pass. Okay, when you have this Gaussian filter, this is always a low pass filter, right?
Right.
You won't get a high pass. So, but you can just get like, for example, if an image is I is an image. Let's say this filter I call it F here. I can have like I minus Fi. This is kind of like a high pass filter. This is a high pass. And so then I can vary this sigma. For example, in this case, like the sigma is bigger, then it will be a less, okay, like, yeah, it will be a, okay, let me don't go into that, but you can play around with the parameter to figure out. So, but you can generate high pass like this, basically. So we want to have a high pass, you want to adjust this sigma for this guy, and then you can have a low pass, also adjust sigma for this guy. So this will be one image, this is I1, this is I2, then you add them together, but you should be weighted sum them together. So
Okay.
maybe some way, maybe like 0.5 or something like that.
Oh, okay. I think I understand. If not, I'll send you a message.
So yes.
So the one that is like right, like let's like you're not having to step away to view the image. So the one that's like the original viewing image, that would be the high pass, and then the one that's far away would be the low pass.
Yes.
Okay, I understand. All right.
Yeah.
Thank you so much.
Sure. So and any other questions? So if not, I will see you guys Thursday, right? Thursday then. Yeah.
See you Thursday.
Yeah. Bye.
Thank you. Bye-bye.